wish I could visit you in person, but we shall have to make do with what we have. So I'll be giving a series of talks this week. So the general topic is safety in AI systems, and particularly SMT-based verification of neural networks. So the plan is to sort of cover the basics today and then go into more advanced topics in the remaining talks. But in any way, because we have so much time ahead of us, please feel free to interrupt with any questions. I'd rather spend more time and hopefully have more of you understand what I'm talking about than just rush through all the slides. So I will try to periodically stop and let you ask any questions, and also feel free to write in the chat window, and I will try to read those questions as well. Okay, so let's get started. So a tiny bit of background, which I imagine will be quite natural to most of you. So today we have software systems everywhere in phones, airplanes, hospitals, and the complexity of this software is increasing. Right, so one application domain that we can keep in mind is autonomous driving, where the software that we need is highly complex. If I asked you to write manually a piece of software that would control an autonomous vehicle, it would probably be a pretty difficult task. And as we know in computer science, and I think as every student knows after taking a few programming courses, manually creating software is very, very difficult. It's highly difficult to get the software to do what you want and not have any bugs. So in the last maybe 10-15 years or so, we are seeing this trend in computer science where machine learning is really taking over the way software is being developed. So instead of having a human stare at the requirements and try to produce a piece of software, we now have these machine learning algorithms where we just take examples of how you want your system to behave, you give them to the training algorithm, and you get back an artifact. This black box that is supposed to satisfy your original requirements. And this kind of programming is really taking over the world, right? If you sit, at least at my university, if you sit at the departmental colloquium, every second talk at least is about machine learning. So this is really a new trend that is achieving amazing results. And domains like image recognition, game playing, autonomous driving, recently protein folding, all of these are now being performed by machine learning. So we might say, okay, well, machine learning is great. Why should we be concerned? So here I have, I think this is, okay. So the problem is that we know that these machine learning artifacts, these black boxes, are highly useful, and they're also very nice because they're accessible to non-experts. You can take a short course on Coursera and quickly learn the basics and be able to train your neural networks. But the fact is that this is not software that was written by people. If you look at these artifacts, at these neural networks, and these black boxes, you don't really understand what's going on inside. And as it turns out, this can be dangerous. So traditionally, we have a bunch of quality assurance techniques that we like to apply on our software. So things like code reviews, refactoring, writing specifications and invariants. And all of these things are very, very difficult to do with machine learning. So it's really not clear what to do in order to become convinced that these black boxes operate and behave as we expect. So now I will try to switch to my short video. I'm never sure how well it comes across using Zoom, but let's try anyway. So what you see here at the front is a Tesla Model S in autopilot mode. The footage is from a car that's driving behind the Tesla. And now pay attention to the left shoulder of the road. So I'm not sure how well you were able to see it, but I'll describe it just in case. So the Tesla was happily driving in autopilot mode until suddenly there was this yellow fence that appeared on the left shoulder of the road, and the Tesla bumped into it. So in this case, it was a pretty mild accident. The Tesla continued to drive, nobody was hurt, so no big deal. But there have already been fatal accidents involving autonomous vehicles, specifically Teslas. Right? So I think this conveys the message, right? If you know that autonomous driving is very, very complex, you're going to use machine learning in order to program it, in order to solve it. And if you're going to be the person sitting inside that car, you really want to be sure that this black box always behaves within acceptable parameters. You don't want it to have any crazy accidents like the one that we saw. Another example of a system where we want to be sure that everything is okay. So this is a system called ACAS-XU. And ACAS stands for Airborne Collision Avoidance System. XU means it's for unmanned aircraft, for drones. So this is a standard that's being developed by the American FAA, the Federal Aviation Administration, which is the organization in charge of regulating air traffic in the US, and consequently, it's a very important organization in the world. And the FAA came to the realization that we have so many drones flying around that we don't want them bumping into each other, so we should have a system that will prevent such collisions. So the system is airborne, so it's mounted on an actual drone. It's called the on-chip in FAA terminology. It reads sensor information about another drone that is nearby. This is the intruder. The intruder does not necessarily have to be malicious. It's just another drone that is in our proximity. And the system reads a bunch of sensor information, so things like speeds, distances, angles, and it just needs to make an advisory. It needs to give the on-chip a turning advisory in order to avoid collision. And the advisories can be either clear of conflict, meaning you can fly straight, there is no need to change your trajectory, there's no risk of collision. Other advisories can be strong left or weak left, indicating that you have to turn left by so many degrees in order to escape a collision. And symmetrically, you have strong right and weak right. So these are the 5 advisories that the system can make. And again, the motivation is just to avoid a collision between the on-chip and the intruder. So I think the statement of the problem is pretty simple, right? We understand what needs to be done. But as it turns out, when the FAA sat down and tried to implement this system, it turned out to be too complex for manual implementation. Right? So it's one of those systems where you can easily solve many of the cases, but the really complex cases where speeds are high and distances are small, they become too complex to solve manually. So what the FAA tried to do, when this failed, they created a huge lookup table. They said, okay, we have only so many possible sensor readings. Let us create a huge table. It was a 7-dimensional table. And every time that we get a sensor reading, we will look at the cell in the table and we will see what's written there. And this will be the advisory. So this worked better than the manual software, but as it turns out, these tables were too large. Okay, they were about 2 gigabytes in size. And when you have this software that you have to install on drones where space is limited, memory is limited, battery is limited, you really don't want a lookup table that is so large. So then the FAA turned to neural networks, and their motivation was compression. So neural networks we will talk about. It's one of those machine learning artifacts, which will be the main topic of our lectures. So the motivation for switching from the lookup table to neural networks was actually compression. The neural networks were only 3 megabytes in size instead of 2 gigabytes. So a very significant reduction in memory. And it turns out that they actually performed better than the lookup table. And the reason is that neural networks are a smooth, continuous function, whereas the table had these jumps in it when you switched from one entry to the next. So the neural networks knew how to interpolate a little better. But of course, we have here now a very interesting situation where you have a very respectable regulatory organization like the FAA. And they have a very safety critical system, right? You don't want any drone collisions. And they want to solve it, they want to implement it using neural networks. So of course, this requires a certification process. We need to be sure that these neural networks behave as we expect before we install them on actual aircraft. Let me stop here for any questions. Usually there are questions on this slide. You can also write in the chat window if you prefer. Okay, so let's continue. So the obvious thing that you can do if you have a neural network and you want to be sure that it's operating correctly is to certify it using testing and simulation. And this is really the standard approach that is being used in the industry. And the way that the FAA did this certification is through encounter plots. Okay, so what you see here is a little diagram that they drew. And here in the middle, you can barely see the on-chip, that's us, remember, and the intruder, that's the other drone. And in order to produce this encounter plot, they fixed many of the input parameters. And then they showed you what the neural network outputs based on the location of the intruder. So if the intruder is very far away, or if it has already passed the on-chip, then it is in the white region. This is the clear of conflict region. So the neural network tells you that you should continue flying straight. There's no risk of collision. If the intruder is in this light green region, right, it's coming at us from the left, then the neural network tells us weak right. If it's a little closer, you get a strong right. And symmetrically, you can get weak left or strong left. So this is an encounter plot, and the way that it is produced is by taking the neural network, again, fixing many of the inputs, and then running simulations. So say sampling 1 million input points at random, seeing what the output that you get for each of them, and then drawing this little diagram. So the problem with this diagram, so the benefit is clear, right? You can sort of see that the neural network operates as you expect. But the problem is that this cannot ever prove to you that there is no bug. Right, so this is usually the problem in testing. You can find bugs, right? If you detect a point here in which the network tells you strong left, then this is a bug. But if you have not found such a point, you are never guaranteed that such a point does not exist. And this is the usual problem with testing. So this is the standard approach that the FAA tried to apply. It's also applied in testing. Let's see that we have a question. Let's see, is there a finite, if there's finite sensory readings and a complete lookup table, then why can't the network not simply be verified by testing? So there is the answer is that the input space is not finite. Okay, so the inputs are continuous, or at least they're almost continuous. Of course, the sensor in the end only have some finite resolution, but this resolution is very, very good. So effectively, you can treat the input as a continuous space. So what the lookup table did was they took the continuous input space and they put a grid on it, and they sampled at the points of the grid. And for each of these points, they said, here you should turn right, here you should turn left. But if your sensor reading turned out not to hit one of the grid points, then you fell somewhere inside the grid cell, and then you would interpolate. You would look at what the nearest neighbors, what were the advisories at the nearest neighbors, and you would use them in order to interpolate the answer for your particular reading. So this is how it works with the lookup table. And the neural networks know how to interpolate better, okay, because their mechanism for handling these cases where you don't hit a particular grid point is better. And of course, they're also significantly smaller. Any other questions? Okay. So now comes verification, right? So with testing, as we said, is good but not perfect. What can you do? So the topic of these talks that we'll be hearing is verification, right? So in formal verification, we want to answer the following basic question. Given a program P and some property phi, does P satisfy phi? So this is the basic question that we ask in verification of software in general, software and hardware. And the verification procedure, when you answer a verification query, it can give you two possible answers. It can tell you one, that the property holds, and then you're happy, you know that your system satisfies whatever property it is that you wanted to check. Or the other option, it can give you a counterexample. It can tell you, look, if you take your program P and you give it as input this X, this Y, and this Z, then you will see that you get a counterexample. Your property does not hold. It is valid. So the main point in verification is that it gives you strong guarantees. Okay, so it's very important to understand that this problem is not like testing. In verification, if the verification engine tells you that your property holds, then you are guaranteed that it holds for any possible input. And this is a very, very strong guarantee. It exactly fills this gap that testing cannot. Okay, so this is not just a finite testing, but rather some sort of proof, a mathematical rigorous proof that a counterexample cannot exist anywhere in the input space. Now, of course, there is a reason that not everybody is using verification, and the reason is that the verification problem is much more complex to solve than testing. Testing is easy, right? It's very easy to do. Every student in an undergraduate course knows that once you finish your software, you run it on some test cases. Verification is more difficult, it's more costly, you need some special skills usually in order to do it, but the benefits are also high. You get a strong guarantee that your system is correct. So verification as a field has existed for about 60 or even 70 years now. There are 2 Turing Awards that were awarded to folks working in this field. So it's a very well-established domain within computer science. And we know, or sort of know, after so many years of work, how to handle traditional constructs that we have in software. So things like loops, if-then-else conditions, go-to statements, function calls, all that stuff. We sort of know what we're doing with those constructs. And we also know sort of what properties we need to check. And so if you give me a C++ software that you wrote, I will likely try to check, assuming I have a verification engine, I will try to check that there are no array overflows, that you don't divide by 0, that there are no null pointer references, a bunch of stuff that I know C software is prone to. So for traditional systems, we sort of have this figured out. Of course, this is far from a solved problem. There's a lot of active research going on, but we have some basic understanding of what to do. And there's also been a lot of work on tools. Because this field has existed for so long, people have really created stable tools, and you can really verify real systems. And now we need to figure out how to do all of these things for machine learning generated software. And because machine learning generated software is new, it's only been around for a very short time, people don't know how to verify it. And because all of its properties are different, there are no loops, there are no function calls. You need new and tailored verification techniques that will allow you to verify these kinds of systems. And the obvious question is it even worth the effort? And I think that it is, especially for safety critical systems like ACAS-XU, like the autonomous driving example that we saw in the beginning. If you have systems where human lives depend on, or a lot of money has been put into, then you really want to be sure that these systems are good. Let me stop again for any questions. So far, so good. So another example, another motivating example of why you want verification in this context. So this one is called adversarial inputs. I imagine some of you are familiar with it. So in 2014, a group of researchers discovered the following intriguing property. We use the word intriguing because that's the title of the paper that they published. So they took an image recognition network. So image recognition is one of those domains in computer science that has been completely taken over by neural networks. And they took a neural network that was state-of-the-art at the time, and they gave it an image of a panda, the image that you see here. And the neural network is a classification network. So there are several options that it can classify the image into. So it chose panda, which is, of course, the correct answer. And it also tells you its level of confidence. So it says, I'm 57% sure that this is indeed a panda. So far, so good. Then the researchers took this perturbation that you see here. So the idea is that you have a small perturbation for each pixel in the original image. The epsilon means that it's a very small perturbation. And you overlay the noise on top of the panda on the left, and you get the image on the right. Now, to the human eye, the image on the right is completely identical to the one on the left. So still clearly a panda. Only now the neural network replies that this is a gibbon. And not does it only make this misclassification, it also does it with 99% confidence. And so it makes a mistake, but it's really, really sure that this is the correct answer. And when this was discovered, this was really mind-blowing, because up to that point, there was some belief that neural networks sort of mimicked the way that the human brain worked. This is also where they got their name from, and that they really understood somehow that this is a panda. And as we found out, this is really not the case. So adversarial inputs has since become the name for this phenomenon where you take an image or an input that is correctly classified, and you add a small amount of perturbation, and this causes a misclassification, like the one that you see. We know now so this is a very active research field. Even 8 years later, there's literally hundreds of papers being published on this every year, maybe even thousands of papers. And we know that it's very, very easy to find these adversarial examples. Given a panda, we know very easily how to find this perturbation that you need to add in order to fool your neuron. You might say, okay, big deal, pandas, gibbons, who cares? So here is another example, this time from autonomous driving. So a neural network trained to identify traffic lights. You start with the image on the left and it says traffic lights, very good. You change 11 pixels, you get the image on the right, and now this is the kitchen oven. So again, I hope that this really conveys to you the seriousness of the problem. Now, these adversarial examples can be produced, as their name suggests, by some adversary. But it can be some malicious adversary that is trying to fool you. And they know how to alter your inputs in order to make your neural network make mistakes. But it can also be random noise. Right? If you install your neural network on millions of cars, eventually there will be some glare from the sun, there will be some scratches on the camera, there will be some rotation, some snow. Images will become distorted, and eventually you will get to these misclassifications, even randomly. So this is really something that we want to be sure that our neural networks are robust to. Okay, so this we talked about. So adversarial inputs or adversarial examples is the attack. When somebody finds an input that fools your neural network. You can also talk about something called adversarial robustness, which is a measure of how resilient your network is to this kind of attack. Right? So an adversary is trying to attack your neural network. They're trying to find an input that will fool it. And if your network has a high level of robustness, this will be very difficult to do. And this is, again, a very active field of research in machine learning. And there have been techniques proposed that will take a neural network and they will improve it. These are called hardening techniques. They will make your neural network more robust. It will become more difficult to fool it using adversarial perturbations. But we know now that these defenses often are tailored to existing attacks. Right? So you sort of have this arms race. Somebody invents an attack, and they show the world, look, we can find adversarial examples. And then the week after, somebody develops a defense. And how do they develop it? They tailor a technique to the attack that they already know. And they show you, look, if you try to attack my neural network now, you will fail, or it will be much more difficult. And then the problem is that the week after, somebody invents a new attack, and this attack breaks existing defenses. So we're in this arms race that's still ongoing. And as it turns out, verification can really be used to establish robustness guarantees. You can use formal verification. Remember that a rigorous mathematical approach for proving properties of neural networks to prove that the neural network is robust against adversarial attacks. And then if you prove this, then even if next year, in 2 years, in 5 years, comes along an adversary that is really, really smart and they have an attack that is amazing, even they will not be able to fool your neural network because you have already proven that it is robust. So if I summarize the motivation that we've seen so far, so we had safety critical systems like AKS-XU, like the Tesla, that we want to make sure that they don't bump into things. We have security concerns, right? We want folks not to be able to attack our neural networks using adversarial attacks. And there are also other use cases that I will briefly mention in the remainder of this series of talks. But all of these are motivation for why we need to verify our neural networks, why we need to be sure that they are correct and robust before we deploy. Let me stop again for any questions. So, roadmap. Okay, so we've said that machine learning is becoming very widespread. We know that there are already problems with systems that rely on machine learning. Certification is a very significant challenge. Organizations like the FAA are now trying to figure out how to certify these systems. And what we will talk about next today and probably also tomorrow is we will focus on just neural networks. So you can think about other kinds of machine learning artifacts, and there have been work on verifying other kinds of machine learning artifacts, but most of the active research is done on neural networks because this is now the dominant kind of artifact that people are using, so we will also focus on that. And first, we will try to understand how the neural network verification problem is defined and why is it so difficult. Then we will survey the state-of-the-art techniques, how people are solving it today. And then we will discuss one of these techniques, ReLUplex, in more detail. So without further ado, let's jump right into it. So what are neural networks that I keep talking about? So this is a neural network. Okay, this is a very grand name for a graph. Okay, so a neural network is a layered graph. The nodes are called neurons, and they are organized into layers. So the first layer is the input layer. This is where the input values come in. So when you evaluate the network, you will assign your input values here. If you think about the AKS-XU example, AKS-XU, this is where you will put your sensor readings. So distances, angles, etc. You will assign the values here. And then the remaining neurons are again organized into layers. So we have this layer here. This is called the first hidden layer, the second hidden layer, third hidden layer, and fourth hidden layer, until eventually you have the last layer, which is the output. And if your neural network is a classification network, which is what we will focus on, then these are the confidence levels for each of the possible labels. Right? So for example, if the AKS-XU system can have 5 possible advisories as outputs, then each of them gets a score, and the one with the optimal score is the winner. This is the advisory that you return to the caller, to the user. So this is a neural network, and the way that the values are propagated through the layers is through a simple arithmetic computation that we will see in the next slides. So the values are propagated from the first layer to the second, to the third, to the fourth, fifth, until they reach the output layer, and then they are returned to the user. Now, these creatures can be quite large. Okay, so neural networks out there can range from anywhere between hundreds and thousands of neurons to millions and tens of millions and even hundreds of millions of neurons. So they can be quite large. And of course, for a human, it's completely impossible to understand what's going on. You look at one of these things and it lacks any kind of logical structure. There's no classes, no functions, no if conditions, no nothing, right? Just a big pile of graph nodes. Okay, so this is what we said verbally just now. So how are the nodes evaluated? So the input layer is given, and then every layer is computed from its predecessor according to two things. So one is the weights, and the other is the activation functions. So suppose we are trying to evaluate neuron V4, and we already have the values for neurons V1, V2, and V3. This can be either that these are the input neurons, or this can be some snapshot of the middle of the neuron. So we already have the values for V1, V2, and V3, and we need the value for V4. The way that V4 is computed is according to this weighted sum here. And so each edge has a weight that is part of the neural network. It's a predetermined weight. You compute the weighted sum of the current assignment according to these weights, and then you apply an extra function f. This is the activation function. And the result of this expression is precisely the value that will be now assigned to V4. And this computation you just repeat for every neuron in the neural network until you have computed your output neuron scores. So what are some of the activation functions that folks are focusing on? So the most famous one, which will also be our focus, is called the rectified linear unit, or ReLU for short. And the way that a ReLU is defined is the max between the input and 0. Okay, so a ReLU can have two phases. If the input turns out to be non-negative, this is what we call the active phase, and the output is just the identity function. Right, so for example, if the input for this particular small example is 0, 2, and 3, the weighted sum that we compute gives us 1. And then when we apply the ReLU function, the input is positive, so the output is the identity function, it's 1. So this is what we call the active phase of the ReLU. Alternatively, if the input is negative, then we say that the ReLU is inactive, and then we get a 0 as the answer. So for example, if the inputs are 1, 0, and 3, we get now -2 as our weighted sum, and the output after the ReLU has been applied would be just 0. So the key point, one key point here is that ReLU is piecewise linear. It's either active, in which case it's a linear function, the identity function, or it's inactive, in which case it's just the 0 function. So it has two linear phases, active and inactive. There are also other activation functions. One famous activation function is max pool, which just returns a maximum between a set of values that you give it as input. There's also average pooling that computes an average between certain values. There's sigmoids and hyperbolic tangents, which are not piecewise linear and are a little less interesting for us today. And really, there are many, many activation functions that you can talk about and be interested in. Any questions on how neural networks are defined? It's a really quiet. So now that we know what neural networks are, how do we verify them? Or what does it even mean to verify them? So here's the definition. Okay, so this is what the neural network verification problem is. For a neural network N that maps a vector of inputs X into a vector of outputs Y, given also an input property P on the inputs and an output property Q on the outputs. So these are all the things that are given. The question is, does there exist an input X0 with output Y0 such that X0 satisfies P and Y0 satisfies Q? In verification terminology, we sometimes call these P and Q precondition and postcondition. Right? So P concerns itself with the inputs. It tells you something about the inputs to the neural networks, and Q tells you something about the outputs. Okay, so there is a question on the previous slide. How do different activation functions affect the verification procedure? I will talk about that later. That's a very good question. So for this definition, so P characterizes the inputs that we are checking. And so let's take as a running example the AKSXU system. And let's say that we want to prove that if the intruder is very far away, the network never tells us to turn right. In this case, we will take P to tell us, to characterize the inputs where the intruder is very far away. These are the inputs that we care about. And we will take Q to be the negation, the undesired behavior that we are looking for. So in this case, we want to prove that the network never tells us to turn right. So we will take Q to tell us that the output is turn right. So we're taking the negation of what we really want. And then we will try to solve this verification problem. If we are able to find an X0 for which P holds and Q holds for the output, then we have what we call a SAT answer. We have been able to satisfy the constraints. We have a positive answer. And this will be our counterexample. This will be a case where the intruder is far away, but the network told us to turn right. So this is one possible outcome. The other is unsat, in which case we know that we can never satisfy the constraints that we have posed, and consequently it is impossible to find an input where the intruder is very far away, but the network tells us to turn right. And so we know that it will never tell us to turn right, which is what we want. So these are the two outputs of the verification problem, and this you can really remember, SAT always means counterexample, right? You get back an assignment that is a counterexample to the property that you're trying to prove. Unsat means that you're happy. You have not been able to find a counterexample, and so you can be happy and tell the person who hired you that the system is correct. Okay, so this is the example that I just gave, right? So if the intruder is distant, then the network always answers clear of conflict. So in this case, we would take our input property to say that one of the inputs, perhaps this input that index 0 indicates the distance, we will ask it to be at least 40,000 feet. And the output property, if Y0 is the clear of conflict advisory, and we want it to be maximal, right? We want, if the maximal output is the winner, we want the advisory for clear of conflict to be highest, then we would, as the negation, take the fact that either Y at index 0 is less than Y at index 1, or 0 is less than 2, or 0 is less than 3, or 0 is less than 4. If we're able to find a satisfying assignment, then we know that we have an input where the intruder is distant, but one of the other advisors is 1. And if we get unsat, then we know that the system behaves as we expect. Okay, so a question in the chat. Don't we need to check that the post condition is satisfied for all inputs that satisfy the precondition? That is precisely what we're checking. Right, so the precondition defines an infinite set of inputs, and the verification problem is to show that you can never satisfy the post condition Q for any of these inputs. Does that answer the question, or perhaps the negation is probably confusing, right? So yeah, so in our case, Q, the post condition, is what we don't want. This is the bad behavior, right? So if you find one satisfying assignment, then you have proven that you have a bug. If no such point exists, then you are happy.
I'm sorry, if you just return to the slide with a definition of, yes, so because you say exists, does there exist an input X0? I would expect here for all inputs X0.
So let's say that you want to prove that if the intruder is very far away, the network never tells you to turn right. So we agree that P should characterize the case where the intruder is very far away. Now the question is, what do we pick Q to be? Or you know what, even better, let's say that we want to prove that the advisory is always clear of conflict. If I take this question and I pick Q to be the advisory is clear of conflict, then I will get back SAT, right? The verification engine will tell me, look, I was able to find a point in P that satisfies your conditions. So it will give me a point where the intruder is distant and the network told me not to turn. This is good, but this doesn't prove that there is no point in which the network tells me to turn. So the way I would be able to cast what I really want to prove into this formulation is to take Q to be the negation of what I want. If I want the network to always tell me clear of conflict, I will take Q to be the network does not tell me clear of conflict. And then if I get unsat, this means that for all points in the precondition, the network always tells me clear of conflict. So this is the negation. Okay, this is a satisfiability problem. If I take Q to be what I really want, I will just get an example where my property holds. If I take Q to be the negation of what I want and I get unsat, then I know that my property holds for the entire space contained in my precondition. Yes, no? I hope that answers. the question. Another question, can we formulate verification problems involving multiple inputs other than just one? Yes, so that's not yes. So in general, in every verification problem like this, the property P can involve the entire vector, right? So if the vector has multiple inputs, then one maybe signifies the distance, another signifies the speed, and a third one the angle. Then you can have a condition that involves all of them. You can say whatever you want on all of your input fields. I see that I didn't completely answer the question. So, verification problem involving multiple inputs. So this is also something that you can do. Remind me of that question later, and I will answer. There is an answer, but I don't want to go into that right now. But yes, in general, you can do that. Okay. So here is how you would cast adversarial robustness into this setting. So remember, adversarial robustness is where we want to ensure that given a point x0 and a given amount of noise, the classification remains the same, right? Regardless of how you distribute the noise. In other words, I say, here is my image of a panda, and the adversary can change. I know it can brighten every pixel by so much. I want to show that it can never cause my network to misclassify the image. So in this case, we will take P, the input property, the precondition, to state that we are only concerned with points around our particular input x0. Okay, so x0 in this case would be the particular panda that we are checking. We would say that for every point that is very close to x0, so the distance is at most delta. And so this is the precondition. It tells us only look at points that are very close to your input point that you're checking. And the output, we would the output property we would set to be that the classification is wrong. Right, so if y at index I0 is the classification of a panda, the one that we really want, then we would have a disjunction that says that at least one of the other outputs is greater. So again, if we are able to satisfy this problem, then we have a counterexample. We have a concrete image that is misclassified. And if the answer is unsat, then we know that we are happy. There is no way to fool our neural network. It is adversarially robust, assuming the adversary is allowed to add this much noise. So here is a theorem, and this connects to the question about the activation functions from before. So for a neural network that has just the ReLU activation function. So remember, we said there are many possible activation functions. Let's now just restrict ourselves to ReLUs. And for properties P and Q that are conjunctions of linear constraints. Okay, so P is just a conjunction. We'll say input x1 is less than 10, input x2 is greater than input x3, and input x4 plus input x5 is at most 10. Okay, so just a bunch of linear constraints, a conjunction of linear constraints on the inputs. And Q is a conjunction of linear constraints on the outputs. Even in this very simple setting, right, so we're really restricting the problem, but even in this very simple setting, the problem is already NP-complete, and it's NP-complete in the number of ReLU nodes. What does this mean? It means that if you have, for example, a neural network with 300 nodes, like the AK6U system, this is how large these networks are, 300 nodes. In the worst case, it will take you, no matter how good your algorithm is, in the worst case, it will take you 2 to the power of 300 steps to verify, which is, of course, very, very bad. So where is this difficulty coming from? So membership in NP is easy, right? If I give you a witness, if I give you a satisfying assignment, then you will just assign it to your input nodes. You will evaluate the neural network, which you can do in time that's polynomial in the size of the neural network. You will evaluate it, and you will see that the input satisfies P and the output satisfies Q. So checking that the problem is NP is straightforward. And the interesting part is how to show that it is NP hard, which we do by a reduction from 3SAT. And I will go over the reduction because I think it exposes where the difficulty is coming from. So to remind you, how is the Boolean satisfiability problem 3SAT defined? So you have a bunch of Boolean variables, x1 up to xn. You have a formula that has k clauses, and the formula is a conjunction. So you have C1 and C2 and up to Ck. And each clause is a disjunction of 3 literals, where a literal is either a variable or its negation. Right? So Q1 here can be either x1 or not x1, or it can be x5 or not x7. Right? It's a variable or its negation. So this is the input to the 3-SAT problem. And the goal is to find a variable assignment that satisfies the formula. So we just need to assign values to the variables in a way that gives you back true for the formula as a whole. And now what we want to do in order to prove that the neural network verification problem is anti-harm, we want to take the input to 3-SAT and transform it into an input to the neural network verification problem, such that the latter is satisfiable if and only if the original is also satisfiable. So suppose now we have a clause and we want to encode it. We will encode the neural network. We will encode the formula that we are trying to check the satisfiability of into a neural network. So if we look at the most basic components of a 3-SAT formula, these are the literals, right? These are either variables or their negations. So we will have a node for each variable. And if we need to use the variable, we will just use that node. And if we need to use the negation of that variable, then we will compute 1 minus that node. So we will assume that the variables are either 0 for false or 1 for true. And if we need a negation, then we will just compute 1 minus the variable that we can just do using a weighted sum. Okay, we will just define the literal q to be 1 minus xj. This will give us not xj. So negations are pretty straightforward to have. How about disjunctions? So remember, when we construct a clause, then we have literals, and then we have a disjunction of literals. So I claim that the following construct is a good way to compute a literal, a clause. So we have here 3 literals, q1, q2, and q3. They can either be variables or their negations. And we want to compute the disjunction of these 3 literals. So I claim that this little construct here, this widget, computes the disjunction. To see this, let's see how it goes. So suppose at least one of these guys is 1. And so one of the literals is 1. We expect the output to be 1. So ti, right, computes minus q1, minus q2, minus q3. If at least one of them is 1, and the others are either 0 or 1, then ti is minus 1 or less. Then we add 1, we add a constant 1, so it becomes 0 or less. Then you have the ReLU function, so 0 or less becomes 0. And then when you compute yi, you take 0 plus 1. So we get 1. So if at least one of the literals is 1, you get 1 as the output. So that's good. And if all the inputs are zeros, then ti is exactly 0. You add, then this contributes 0. You add 1, and ti becomes exactly 1. And then you have minus 1 plus 1, you get a 0. So in other words, if all of the inputs are 0, you get a 0, otherwise you get a 1. So this is precisely the disjunction of these literals. So we have negations, we have disjunctions. The only thing remaining is conjunctions. So suppose now we have the outputs of our clauses, and we want to compute the conjunction. We want to return true if and only if all of them are satisfied. So how will we do it? We will just take the sum, right? So remember, 1 means that they're true, that they're satisfied, and 0 means that they are not. We need all of them to be satisfied. So we will just compute the sum and call it y. And then as the output of the network, we will select y, and the output property will be just that y equals exactly n, where n, remember, is the number of clauses. And this will be satisfied if and only if all of the conjuncts are exactly 1. Right, so if I put it all together, we have for each of our inputs, we have an input variable to the neural network. We will compute the literals, then we will compute the clauses. For each clause, we will have a single variable that represents the outcome. We will sum over these clause outcomes and compute the final output y. And the network will be, and the verification problem will be to find an input assignment for which y is exactly n. If we're able to find such an assignment, this means that we have a satisfying assignment for the original formula, and if not, then there is no such assignment. There is a small debt here that I'm not going to go into, right? So I said that we stipulate that the input variables are either 0 or 1. So this is not a linear constraint, right? I said that we're only talking about a conjunction of linear constraints, and this is a disjunction. It's either 0 or 1. It's not a conjunction of constraints. There is a way to solve this little difficulty, but I don't want to go into it right now. But hopefully you will believe me that you can circumvent this little difficulty using a simple trick, and then the reduction works and the problem is actually complete. So any questions so far? No. Okay. So now, again, going back to the question from before, so I only showed that the problem is NP-complete for a simple network that has only the ReLU activation functions. You might say, okay, well, maybe ReLUs are complicated. Maybe if my neural network has max pooling, it will become easier to verify for some reason. So no, as it turns out, the verification problem remains NP-complete, even if you allow P and Q to have arbitrary Boolean structure. And the proof for this is you can add a few more neurons to your neural network to express arbitrarily complex input and output properties. And so it is enough to focus just on conjunctions, because we know that you can reduce disjunctions and negations into conjunctions, actually, as we've seen as part of the proof. And also the activation functions are not important. Specifically, for every piecewise linear activation function, all of them are reducible to the ReLU case. Right? For example, right, ReLU and max are completely interchangeable. ReLU, by definition, you can express as max. Right? ReLU is defined as the max between x and 0. But also, if you have a max between a certain set of variables, you can express that using ReLUs. For example, if you need the max between x and y, you can just compute the ReLU of x minus y and then add y. If x is greater than y, this will return x minus y, plus y will give you x. But if y is greater than x, this will give you 0, and then you are left with just y. So really, all of the piecewise linear activation functions that you can think of, ReLUs, leaky ReLUs, max pooling, absolute values, all of these you can translate into ReLUs, so it's really enough to focus just on ReLUs and just on conjunctions of linear constants. There is an announcement chat. Okay. So there are also other activation functions that are not piecewise linear. You have sigmoids, you have hyperbolic tangents. These questions are a little more complex to solve. They have received some attention in the literature so far, but not much. Okay, folks have mostly focused on verifying networks with piecewise linear activation functions because these seem to be quite dominant. Still, there is some work on verifying also non-piecewise linear functions. One way to do it is by approximating these functions with piecewise linear functions and then reducing the problem back to the setting that we see now. So to summarize what we've seen so far, so we know now that neural network verification is hard, it's NP-complete, even for simple networks and simple properties. We know also that real networks can be quite large. Right? I said that neural networks can have thousands and tens of thousands and even millions of neurons. So right, if we were naive, we would say, okay, there's nothing to be done, right? We should call it a day and go do something else. But as it turns out, verification people are not concerned about this kind of hardness result because we know that on average, the neural network that we will need to verify will not exhibit this terrible behavior. So next, we will talk about state-of-the-art verification techniques, how people have been trying to tackle this problem, which appears quite difficult. We will focus on one such technique called ReLUplex. Hopefully, we will get to it today. If not, then tomorrow. And this is the plan. Any questions so far? Okay. So what are some of the techniques that folks have been using? So here, there's a disclaimer. Okay, so this is a field that is quite new and it's moving forward quite rapidly. So I have some slides here, but obviously I won't cover all of the verification approaches out there. So apologies if your favorite verification work is not cited here. There's really too much to show in just one presentation. So the main challenge, as we saw, is scalability. Okay, we know now that the neural network verification problem is NP-complete. It's very difficult to solve. And the main challenge that everybody is struggling with is scalability. We want to be able to verify networks that are very, very large. This is usually the case in verification. This is fine. Now, this is a new field and it's improving and the scalability is improving quite rapidly. It's quite common to distinguish between two kinds of techniques. One is the sound and complete kind. And when we say that a technique is sound and complete, we mean usually that it will always succeed. That if you give it a neural network verification problem, it will always be able to solve it given enough time. Okay, these techniques tend to be a little slower, so their scalability is more limited. This is the sound and complete techniques. Then the other kind is the sound and incomplete techniques. These are techniques that have better scalability. They are more lightweight. But the problem is that they may return don't know. Usually what happens is that they can return SAT. Well, actually not. So they can either return SAT or unsat with certainty, but usually not both. So some techniques will tell you SAT, and if they tell you SAT, then they are correct, and you can stop. But if they might say don't know instead of unsat, and some techniques will reliably tell you unsat, but will fail to solve SAT instances and will reply don't know. So these are the sound and incomplete techniques. Usually they are sound in the sense that if they tell you something that is correct, but they may say don't know, in which case you obviously don't have an answer. There are some orthogonal techniques that we will talk later on this week. Specifically, abstraction techniques is a very interesting field. We will talk about it. It's orthogonal to completeness. And also there is a lot of related work on testing, on coverage, all very interesting stuff that I won't have time to cover in these talks. The usual question that I get at this point is, okay, well, you have spoken to us about NP hardness and average cases, but really, tell us now, give us the numbers. How large is the network that you can verify? So there's a bunch of disclaimers, and then I'll tell you the answer. So the disclaimers are that it's very, very difficult to compare. Okay, there are different properties that make a huge difference. For example, adversarial robustness properties. These tend to be actually quite simple. So a lot of verification techniques that can operate quite quickly on adversarial robustness properties may fail to solve to quickly solve other properties. So it's not just the size of the neural network, it's also the properties that you're working on. There's again this thing of complete and incomplete techniques, right? So incomplete techniques, if you say they can verify networks with X neurons, they're not always able to verify these networks because they might say, I don't know. Is that also an acceptable answer? There's a lot of implementation variants out there and variability out there, and people are using different benchmarks. So all of these are the disclaimers. And still, as a rule of thumb, I would say that today, complete techniques can scale up to tens of thousands of neurons. Again, all of the disclaimers above apply, but in general, tens of thousands of neurons. And incomplete techniques are now at the happy point where they can even scale to hundreds of thousands of neurons. So there have been some cases where networks with hundreds of thousands of neurons have been verified using incomplete techniques. So I think the state of the art is very rapidly improving. And so this is one of the slides that I change between these talks occasionally. So back in 2017, we could do hundreds of neurons. Now we're a few years later, we're already at hundreds of thousands, which I think is very nice. If there are any questions on this, please go ahead. Otherwise, I will start a short survey of past techniques. Okay, we have a question. Are incomplete techniques those that don't verify for all inputs? So yeah, so you can always pose any question to these incomplete techniques, but typically what will happen is that they will either be able to solve your query and say SAT or unsat reliably, or in many cases they will just give up and say I don't know. So these are the three possible outcomes from an incomplete technique. A complete technique only has two possible outcomes, SAT or unsat. The complete technique can also say I don't know. I give up, I can't solve it. So now let's see what folks have been up to. So actually there is one very early paper, from 2010 by Polina and Takela, and these were really this was one of the first attempts to verify neural networks. There are a few other papers that came earlier, but this is really an important milestone. And these guys actually focused on networks with sigmoid activation functions. So we said that today mostly the focus is on piecewise linear functions. Here they actually started with sigmoids, and the main idea was to over-approximate sigmoids using interval arithmetic. So this is actually a very important concept, this over-approximation. So I will spend a couple of minutes explaining it. So the idea in over-approximation, which we will talk about also in greater detail later in this week, is to take a system that is for some reason very difficult for us to verify, system S, and replace it with a simpler system, S bar, that we can verify more easily. And the idea is to always make sure that all of the behaviors of S also appear in S bar. But S bar may contain also additional spurious behaviors that do not exist in your original S. And because S bar is simpler to verify, we verify it instead of S. We verify S bar. And then we are sometimes able to draw conclusions about S. So suppose we start with some system S, and suppose its shape is a ball. And for some reason, ball-shaped systems are very difficult for you to verify. You over-approximate it with another system, S bar, that is the orange square. And suppose that for some reason, squares are very easy to verify in your world. So you have over-approximated S by taking a system S bar that contains all of the behaviors of S. Then you verify S bar. What does it mean to verify here? It means to prove that all of the behaviors of S bar are correct. If you're able to show it, then because S is contained in S bar, all of the behaviors also exist for S bar, then you know that S is also correct, and you are happy. But if S bar turns out to be incorrect, then you have two options. Either S is also incorrect. And this will happen if you find a counterexample that is also a behavior of the original S. In this case, you can say SAT and you can stop. But it is possible that you detect what we call a spurious counterexample. You detect a bad behavior which is in S bar but not in S. And when this happens, you are not able to know whether S is safe or not. And what you typically do is a step of refinement. Intuitively, what you do is you take the orange square and you make it smaller so that it excludes the green point that you have found. You make it smaller so that it excludes the spurious counterexample and you repeat. This is the basic concept, and we will talk about it in greater detail later in the week. But how does it connect to the work of Polini and Tekela? So what they did is they took this hyperbolic tangent, or sigmoid, which is this S-shaped function, which is difficult to verify, and they said, let us approximate it using rectangles. Right? So instead of saying that the output of the sigmoid is just this S-shaped line, they say the output of the sigmoid is in one of the orange rectangles. Now, of course, this is a very crude over-approximation because these rectangles are large, right? So you can get an output that is not really an output of the sigmoid function. But this is precisely what an over-approximation is, right? So if you get answered for this over-approximation, you're not able to solve the problem, even if you only assume that the output is in one of the orange rectangles instead of the output of the actual function, then you know that the original problem is answered. So Polini and Tekela implemented the system, and then they gave the resulting problem to an SMT solver in order to solve it. And this was a very nice first step, but they could only tackle very small networks with about 10 neurons, which is a little too small to be of much use, but still a very interesting initiative. Then there were about 5 or 6 years of silence, and then in 2016 there is another important paper by Osbert Bastani and colleagues, and this is actually not a paper about verification. Okay? This is a paper about evaluating a network's adversarial robustness. And what they showed was a reduction from a verification-like problem to linear program. And this, again, is not a paper about verification, but it's sufficiently important to merit a couple of slides here in today's presentation. So what is linear programming? This will also be important for us later. So a linear program, if you're not familiar, is a problem that looks like this. So you have a set of variables x, you have a function c times x, right? So this is just a set of scalars, a vector of scalars that you multiply with x. And this is a function that you need to minimize or maximize, it doesn't matter, subject to a set of linear constraints. So a times x equals b, when a and b are just fixed, matrix and a vector. And you also know that all of your variables have lower and upper bounds. So basically, you have a bunch of restrictions on the possible assignments that you can select for your variables. And under these restrictions, you want to minimize an objective function, and either minimize or maximize it. So this is a definition of a linear program. And okay, so we said this. And linear programming has been around for 70 years now, I think. So it's a very famous problem in computer science. We know how to solve it very, very well. There are very efficient techniques for solving it. So what did Osbert Bastani and colleagues do? So they said, okay, let's look at the neural network. And as we already know, the ReLU constraints are the problematic component in the neural network. We saw that the problem is NP-complete in the number of ReLUs that we have. So remember that each ReLU has two possible phases, two possible linear phases. Either it's in the active phase, which you can express using linear constraints. What does it mean to be in the active phase? It means that the input is non-negative and the output is the identity function. So these are two linear constraints. Or it can be in the inactive phase, in which case x is non-positive and y is 0. So again, conjunction of two linear constraints. And because each of these phases is linear, there is something simple that you can do. If you know that the ReLU is in a specific phase, if you are for some reason certain that the ReLU is either active or inactive, you can throw away the ReLU constraint and just replace it with a linear constraint. And as we just said in the previous slide, linear constraints are very, very easy to solve. So what did they do in this paper? So they said, we want to find an adversarial input around some point x0. So let us encode the neural network. Remember, a neural network has weighted sums in it. So let's encode each of the weighted sums as a linear equation. Let's evaluate the network for this particular x0, this particular image of a panda. And for every ReLU in the network, we will have one of two cases. For this particular x0, either the ReLU will be active, in which case we will write the constraint that the ReLU is active. We will say x is greater than 0, y is equal to x. This is the active constraint of the ReLU. And if the ReLU is inactive for this particular x0, we will replace it with the inactive constraint. And once we do this, the entire verification problem becomes a linear problem, right? Because the searching for an adversarial input, as we saw in the beginning, you can express as a set of linear constraints. The weighted sums in the neural network are again linear constraints. And once we replace each ReLU with a linear constraint, you get a set of constraints that is completely linear, and you can just invoke an off-the-shelf LP solver and have it solve it, and have it find an adversarial example for you if one exists. And this they evaluated on image recognition networks. This was quite successful. Right? So you could verify, well, not verify, but you could find adversarial examples very well with this approach. Right? So this is very efficient, and it's efficient because LP solvers are very fast, and they are mature tools, and it's also sound. Right? If it tells you, look, I found a counterexample, then that is correct. But it is incomplete in the sense that it may fail to identify some adversarial examples. And in order to wake you up, I will ask, does anybody know why? What kind of adversarial examples can you miss like this? No volunteers? Okay, so I will reveal the answer. Right, so the problem is that you may miss adversarial inputs, and the reason is that you are fixing your ReLUs into one of their phases. Right, so suppose that you have a ReLU that is active, but it's active for very, very small value. Maybe it's active, but its value is 0.0001. It's quite possible that there is an adversarial example that is very close for x0 to x0, but for which the ReLU will become inactive. Instead of 0.0001, it will be minus 0.0001. But because you are restricting your encoding to enforce that the ReLU is active, you will not find that example because you will not consider any X's that are negative. So if you find a counterexample like this, if you find an adversarial example, it is truly an adversarial example, but you may miss some others because of these restrictions. So the natural thing that you can do with this reduction for that you can do with this technique from Bastani and colleagues' paper is to extend it into a complete technique, which is what we did in the ReLUplex paper that I will talk about later. And the intuitive way to do this is using case splitting. And so case splitting is basically an enumeration of all possible phases. So for each ReLU, first you guess whether it's going to be active or inactive. You get an LP, a linear problem that you can solve, a linear programming instance, you solve it. If you find a satisfying assignment, then you say set. Right? You have found a satisfying assignment that is correct and it satisfies all of your constraints, then you can stop. But if you are unable to find a satisfying assignment, right? If you are unable to find an adversarial example, then either there really isn't a satisfying assignment or simply your guess was incorrect. Right, you guessed the phases of the ReLUs, but your guess was incorrect, and so you weren't able to find it. Precisely what we just saw in the paper by Bastani. So you have to go back and you have to try another guess. And only if all of your guesses are exhausted, right? So only if you tried all the possible combinations of activation phases and you weren't able to find satisfying assignment in any one of them, only then do you stop and say answer. So intuitively, this is very similar to the naive algorithm for Boolean satisfiability. That you have a formula with Boolean variables and you need to check all of the combinations. You assign one to true and then to false, and you need to check all the possible combinations. And the number is, of course, exponential. So another way to think about this case splitting is like a search tree. The problem is SAT if and only if there is at least one leaf in the search tree that is SAT. Right, so suppose you have a network with two values in it, y1 and y2. You have a search tree, and the root of the search tree, you have not made any guess yet. When you go deep, one layer deeper, you are guessing the phase of one value, the first value in this case. You would either guess that it's active by saying that y1 equals x1 and x1 is non-negative, or that it is inactive by saying that y1 is 0 and x1 is non-positive. So this is the first layer, right? So you guess on one value and you go down one layer. Then you have another layer, so you need another value, so you need again to guess active or inactive. And in this final layer, you have the leaves. Right, so every leaf is a pure linear program. There is no value anymore, only linear constraints that you can solve. If you have at least one leaf that is SAT, then the problem is SAT. And if all of them are unsat, then the problem is unsat. Any questions? Okay, so this is the intuition also for why the problem is incomplete. Oops, what did I do? I jumped to the end. Hold on. Okay. So if you do this case splitting approach where you check the entire search tree, you immediately get an approach that is sound incomplete. Okay, so this is what we proposed in this paper from 2017. And we know that this approach is very, very sensitive to heuristics and tricks for trimming the search space. And so we know that the problem is NP-complete. So in the worst case, we would have to search the entire search tree. But there are many heuristics that you can use for trimming the search space and eventually not having to cover the entire search tree. And then you have a lot of different variations that people proposed. So I have the planet solver. This one is called MIP verify. This other paper. Then you have the BAB solver and other papers by Lugushu and Majanti and the Sherlock solver and a whole bunch of other papers since then that implement different variations of this sound and complete approach. So all of the sound and complete solvers in the end typically resort to traversing the search tree, but they employ all kinds of tricks in order to shrink this tree as much as possible. So this is the family of the sound and complete solvers. Then you also have the incomplete solvers. So one famous example is the DLV solver from 2017. And DLV, what it does is apply discretization of the input space. Right? So they say basically, look, we have the input space that is so large and we have to traverse all of it in order to find, for example, adversarial examples. We can't do it. So instead, let's discretize it. Let's say that we only need to consider a finite number of points, and then let's check these points in a clever way. I have a question. Can you repurpose the verification optimizing heuristic to optimize the neural network itself? Sort of how over-approximation may hint to a valid quantization of the network. So yes, so there is a way. Okay, so one naive way to use verification for optimization is to do a binary search. Right? Suppose I have a single output to my neural network and I want to answer to find its maximal value. I will just do a binary search. I will ask, is it possible that y is greater than 10? If not, I will ask, is it possible that y is greater than 5? Then I will continue this binary search until I am able to find the optimal value up to a desired precision. So if you know how to solve the decision problem, then you can also solve the optimization problem. Of course, this is not a very useful way for solving the optimization problem, and there are dedicated tools that will optimize a neural network for you using a verification technology. Not many tools. Okay, this is not the main focus of the community yet, but I think this is also a very interesting problem. So I hope that answered the question. Okay. So back to DLV. So this guy said, okay, the search space is so large. Instead, let us discretize it, and this discrete space can represent camera scratches, rotations, etc. So you specify the kind of things that can happen to your inputs, and these are exactly these manipulations. So this is sound in the sense that if you find a counterexample, then it is a true counterexample, but incomplete again in the sense that you may miss counterexamples. Right, so this is an image from the paper, the figure from the paper. You start with some initial point, and your set of manipulations, which is again the rotations, the camera sketches, they define how your input point can change. So it can jump to this point, it can jump to this point, etc. And then they traverse the search space until they're able to prove that all of these points are safe. All of them are classified correctly. So this is the DLV song. Then there is a very well-known work from ETH in Zurich by Garrett al. And here the idea was to over-approximate. So much, it's the same principle like in the work by Polina and Takela, where they over-approximated the activation functions. But here, what they over-approximate is actually the input property. Right, so the idea is they say, look, if you think about the input to a neural network, or the input to a single layer, we can think about it as a geometric shape. Right? If I have 2 inputs, then it's a shape in 2 dimensions. If I have 10 inputs, it's a shape in 10 dimensions. But still, it's a shape. And what we want to do is to see how it is propagated through the layers of the network. So maybe my input domain was this blue square. When I pass that blue square through a single layer of the network, it will maybe become this blue rectangle. So this is an over-approximation. Okay, so these shapes can contain points that you cannot really get from the neural network, but this is the same principle as before. If you can prove that all of the behaviors of these rectangles are correct, then you know that the behaviors of the neural network are correct, because these behaviors are contained in this larger geometric shape. So this is also sound and incomplete. This time it's in the other way, right? So it will soundly say that your system is safe. It will soundly say unsafe, but it may fail to detect such examples. Right. And then there's also a bunch of other techniques that I will mention only very, very quickly. So folks have tried to say, look, neural networks, you can regard them as a continuous function. So let's try to do all sorts of numerical analysis based on Lipschitz continuity. So there's a few papers that try to take this route. Folks are focused on verifying binarized neural networks, which are neural networks that have 1 bit to represent each weight. So you have Boolean weights. So this is also an interesting problem. There are verification approaches using quadratic solvers and other over-approximation techniques. There's work on supporting different distance matrix like L0, and also a lot of work on parallelizing and using GPUs in order to verify neural networks. So really a lot of interesting work going on. And like I said, there's so many papers that it's really impossible to even mention all of them, let alone discuss them deeply. And one finally interesting line of work is what we call synthesis. Right? So instead of training a neural network and then trying to verify that it is correct, there is a line of work that seeks to train a network that is correct by construction. So in the formal methods community, we usually call this synthesis. So there's some interesting papers from Google DeepMind and from some other research groups on this stuff. So also a very interesting direction. Okay, so to summarize what we have so far, so we know that neural network verification is really hard, right? It's NP-complete even for simple networks and simple properties. We know that it is reducible to an exponential sequence of easy problems, and these are the leaves of the search tree. We have exponentially many leaves, but solving each of them will be quite simple. So an exponential sequence of very easy problems. This approach is sound and complete and depends on the heuristics that you use, and then you can trade completeness for better scalability. Right, so this is the stuff that we saw, like discretization or abstract interpretation, all kinds of tricks that you can do that are not necessarily complete, but they will give you faster performance. And of course, you can also combine these things with abstraction, that we will talk more about that probably tomorrow. So what I'm going to do next is talk about ReLUplex, but I see we have only 10 minutes left. So maybe I will just give you a brief introduction and then we will stop and we will pick it up tomorrow. So ReLUplex is one of these sound and complete approaches. It was proposed by myself and these colleagues that you see here in 2017. And that project was actually supported by the FAA and the Intel. So the FAA actually came to us with the problem of the AK62 system, and they needed to verify it, and then we developed the algorithm that could verify it for the first time. So I will tell you about that tomorrow. Okay, so let's just do the first 2 or 3 slides. So the idea in ReLUplex is to develop an SMT solver. I don't have the time to go into what SMT solvers are, but these are general purpose tools that you give formulas to and they tell you SAT or unsat. They can handle Boolean structure, arithmetic, strings, and a bunch of other stuff, and arrays and bit vectors. And what we wanted to do was to develop a dedicated SMT solver for quantifier-free real linear arithmetic plus values, which is precisely what you need in order to verify a neural network with ReLU activation functions. And it's based on an algorithm called simplex for solving linear programming. So simplex is one of the earliest techniques for solving linear programs. It's a very well-known and very successful algorithm. And we extended it to support ReLUs, and this is also where the name comes from, ReLUplex. And the key idea that we took was looking at the search tree, instead of doing an eager split. So instead of saying, okay, let's immediately jump to a leaf and try to solve it, what ReLUplex tries to do is to solve things lazily. Right? So instead of going all the way to the leaves, it looks at the intermediate nodes of the search tree, and it tries to solve the problem already in these nodes without guessing, without doing case splitting on all of the ReLUs. And as it turns out, when you defer splitting for as long as possible, you often don't have to split it all. So this really reduces the number of case splits that you do, which is crucial. And I think perhaps that this is a good place to stop today and then pick this up tomorrow. So if you have any questions, this is a very good time.
Is there sort of a connection to, if you think about one-way hash functions, are there any sort of neural networks that sort of look like one-way hash functions that might make it difficult? And do they make it difficult to find verification conditions?
So that's an interesting question. I'm actually not aware of any such connections. Yeah, I'm not sure. I don't think anybody is trying. So I know hash functions are very important for cryptographers, right? And I don't think neural networks are used in that context, maybe for scrambling, but I don't think they're used for encrypting anything.
Because I would imagine if it sort of looks like a hash function, then its output might not be that useful for the initial purpose, which is usually to classify something.
Right. Yeah, I'm not aware of any such connections, but I'm sure somebody has looked at it.
Okay, thank you. I will perhaps stop recording the lecture just now, just in case anybody wants to ask a question, but is camera shy?
Also, remember you can write your questions in the chat.